All right, so now we're going to look at some problems where we handle conservation of energy when it comes to electric potential. So the general idea is when you have a system of charges, you look at work as a change in energy. However, often the system includes all the charges. Maybe or maybe not. If you have a bunch of charges that are moving, you might include all the charges, but maybe not, say, external fields or potential. Okay, so the core idea is we are going to use work as a change in energy. It's going to just depend on which one we're going to use, whether or not the system includes everything and thus conservation of energy applies, or if we have some things outside of the system, in which case we just use work as the change in energy. And what we choose kind of just depends on what's available to us based off of the scenario of the problem. So often we lose electric potential energy, we gain kinetic energy. So let's look at a few examples here. So we have two charged particles of the same mass and charges Q1, Q2 as shown above. The first charge is fixed in place and cannot move. So this guy's fixed. He's fixed. Second charge is released from rest. What is its speed when the charge is a distance 2L away? So generally speaking, what's happening is this thing's going to be pushed away from this guy and going to end up over here. Okay, so if we think about the system of the two charges, there are no external forces on the system. Yeah, they push on each other, but if we think of the system as being both charges, then the external work is going to be zero, and we're going to use conservation of energy. So we're going to look at, like, so the work is the change in energy, but then there's no external forces. This is zero, so the change in energy is zero. So we just think about what's the energy we have initially. Now, the system has two charges. Therefore, there are two forms of energy we're going to consider. Right, we're going to consider the electric potential energy and the kinetic energy. Initially, they're released from rest, so there's no kinetic energy, right? So then, but what do we think about the electric potential energy? It's going to be K. Let's see. It's going to be K Q1 Q2 divided by the distance between them, right? And then the final potential energy, when this thing's way out here, he has some speed here. This guy's fixed, so his velocity is zero the whole time. So we do have some kinetic energy. We want to know this guy's moving at speed v. And then there's still some electric potential energy between the two, divided by 2L, like that, right? So that's the energy there, and we're just going to set them equal to each other. K, Q1, Q2 over L. We're going to subtract this over to this side, right? Because we're looking for solving for the 1/2 mv squared, or we're solving for v. This minus this is like one of these. This is like 1/2. So we're going to be left with 1/2. If you factored out the K, Q1, Q2 over L, you're going to have 1 minus 1/2. That's 1/2. The 1/2s will cancel. Divide by m. Right? And then v, you just take the square root of this. It'd be K, Q1, Q2 over ML, right? So make sure you understand the setup, and then the rest is just some algebra. What's the speed of the charge is very far away. So very far away is, now we say the energy is just kinetic energy. Because if the denominator, if this is really, really big, this is almost zero at that point, right? Because we're saying, oh, we have only kinetic energy left because the distance is so far that the electric potential energy is almost zero. So that's going to be equal to whatever the initial energy was, K, Q1, Q2 over L. And then multiply by 2, divide by m. So you get v squared is going to be 2K, Q1, Q2 over ML. And then the v would be the square root of that, 2K, Q1, Q2 over ML. Like that. Okay. Let's say a charge with mass m and charge q is moving to the right, initial velocity v0, right? So m and q is moving to the right, v0. It's subject to an electric potential difference of delta v. How fast is the charge moving then? So now we're going to talk about there's an external force, right? An electric potential difference. There's going to be some kind of external. There's something that is there. There's something external that's happening there, right? Because now it's that electric potential difference is due to some external charges. So the system, we don't know anything about that. So the system is just going to be our one charge, right? And so what we want to think about is what is the work is the change in energy, right? And so what is the work done by that electric potential difference? All right, so what that means is the work is Q times the change in potential here. Now, I always like to think about this sign. Should the work be positive or negative? And one way to think about it is, do I think that the charge should be going faster or slower? Now, let's say this change in potential were positive. So it's a positive. That means we're going from lower to higher potential. Okay. Now remember, the electric there's several ways you can think about the electric field points from higher to lower, and this is, say, a positive charge. We'll just assume it's positive for right now for the purposes of this analogy, just to get the signs correct. So let's say positive charge is a positive potential difference. Then a positive charge, when it goes from lower to higher potential, should slow down, should move slower. Okay, so this Q times the change in potential probably should be a negative, because we should expect to have less energy, the change in energy. We want to end up with less energy than we had before. 1/2 mvf squared minus 1/2 mv0 squared. That's the change in kinetic energy. Because the system is just one charge, all we have is kinetic energy as part of it. So the Q in change potential should be a negative, because we should have lost some energy. So then what we're going to do is we're going to move the 1/2 mv0 squared to the other side. So 1/2 mv0 squared. We're going to lose this much energy, and we're going to be left with this final kinetic energy. Multiply by 2, make that 2, and then divide by m, and then take the square root. So it'd be square root of mv0 squared minus 2q change in potential over m. And that makes sense that we should have lost some speed given what we just described here. Now, usually they'll be more clear on an AP problem, probably a little bit more specific on terms of the signs and the potentials, but that's one way I try to reason out whether or not I think the answer should be positive or negative based off like my just general intuition or general understanding of how forces and electric fields and potential operate.